We're trying to make it so I don't have to take the last test because he drops the lowest test.
Yeah, I'm gonna need to take it because I didn't do too good.
I'm trying to make the
You
last
got that
test the
out.
one that I dropped.
Yeah. Huh?
Mr. Washington.
Yeah.
He's good.
Yeah, he's really nice. He explains things really clearly, I think.
Man, I should say, I took Mr. King.
Yeah, it took Dr. Ping too. It's kind of hard to understand.
I had
Like,
to
you gotta
really
get
Isn't
around
that
for
like
it.
the Chinese dude?
Yes.
Yeah.
It's so funny. He's like, Calculus 1. I was like, what is
Yeah,
that? I
he's
could
so
not
sweet.
I love his
understand.
class
He's
though.
awesome.
He has like some works, like he's like explaining things, and he was like, I don't know. And then he moves on.
No, he just couldn't understand why we didn't understand. Like, why you know math? I'm like, I don't know, dude. I just don't understand it. I remember,
You know that has
I remember him telling me that. I was like, I just don't get it, man.
He's really chill.
I was a professor in grad school that he'd been in the U.S. for 10 years, but he raised and educated in Poland, but still had a very thick accent. And it was a general relativity class,
Oh.
the course that kicked my butt, and he started talking about the theorem of Pythagoras. And I'm going, all right, Pythagoras, who is Pythagoras? And he looked at us, and there were blank looks at all of our faces, and he goes, you know, and he was really frustrated. Pythagoras, come on. A squared plus B squared equals C squared.
Aw. Really funny.
Oh my god.
What is general relativity? Can you like explain it in like words that I could understand? 'Cause I
Alright.
have a textbook on that at home. Like just because I picked it up because I thought it was kind of cool.
I think it would be.
Is this the thing that Einstein had?
Yeah, he figured out the principle of it in 1905, and then it took him 10 years to figure out what math to go with it.
Okay.
All right, so here's the basic principle of it.
Okay.
That if you are in a closed room
Okay.
and there's a scale sitting there and you stand on the scale,
Okay.
if this room is on Earth, you would measure your weight.
Okay.
It would seem so you could do an experiment, and it looks like the acceleration is 9.8 meters per second squared.
Yeah.
If you were out in space on a scale, and the room were, again, you have no knowledge of what's outside, and the room is accelerating at 9.8 meters per second squared, the scale would read the exact same thing.
Okay.
So whether the room is on Earth or the room is just accelerating at that rate, it would appear the same.
Okay.
And there is no test that can tell the difference between these two situations.
And that's what general relativity is.
All right. The principle is that if there is no test that can tell the difference, then they're identical.
Okay.
Take it to the next step. If I shoot a laser light across, so if I'm just in a room that's still no acceleration,
Yeah.
and I shoot the laser's just gonna go straight across. If I'm in this situation and I shoot it, well, this is accelerating, so from my point of view, or inside the room, it will look like the beam does that.
Yeah.
If this will happen in a room that's accelerating like this, then it should happen here too. That the object will curve just
Yeah.
sheerly from the fact that there's this gravitational this mass here. From this, you establish that what masses really are doing is not necessarily attracting, they're warping space and space itself,
Oh.
and things are sort of gravitating towards the low part of the well. Just imagine it in multiple dimensions, but.
Just imagine it in multiple
I mean, if you take a
dimensions.
trampoline, throw a bowling ball into it, it warps the trampoline, so anything near it will get sort of sucked towards it.
Yeah.
Put that into 3 dimensions, and that's basically what's going on. That the sun creates a warping in space, causing things to, well, if I've got this let's do the 2-dimensional model here. So ball on the trampoline, it sort of bends this like this. It is possible that theoretically I could take an object and throw it this way so that it would actually orbit.
I've seen a video on that before. It's really
Oh,
cool.
man.
Yeah.
Like the coin funnels.
Yes.
Yeah.
Light doesn't have mass, right?
Right, it has no rest mass, it does have a mass equivalent in certain situations.
Oh, okay, so that's why it works.
Well, but the warping, generally I see with light, it's like gravitational lensing, that you take the mass here and it warps it, so, you know, if you're cruising along that space, you don't notice the warp. And so you travel in what you think is a straight line, but it's actually curved. And so light, moving along fast, dumb and happy, comes along, it gets to the warping, and it will move curve. Not like, again, things will travel in a straight line, but so if I had some object, light coming in from both sides, they would bend and meet at a single point. And then from the observer point of view, it looks like that object is in two places. Or in 3 dimensions, it looks like it's in a ring.
Oh, that's why it's the
Why don't-
area relativity.
why wouldn't it just-
Relative to the perspective you're at, it changes what you're looking at.
Yeah,
One person might see this, another view might see it differently.
definitely, as well as there are some things that do change, not, like time changes depending on how fast you're moving. That's in the special relativity. So special relativity versus general relativity. Special relativity is acceleration is 0. So you're dealing with what's called inertial frames. And in general relativity, you now bring in acceleration. So GPS satellites take into account special relativity because they're traveling at some speed, and GPS satellites would be off. It's either 3 meters a day or 30 meters a day. I can't remember prior calculations because of the speed it's traveling. But then there's also, it'll be off because of the warping of space because of the Earth.
So they already put all this into practice.
Yeah, so those two things are taken into account for GPS satellites.
That's kind of insane.
Yeah. So
If you-
we are getting close to my limit of knowledge of general relativity here.
Okay, is that saying that, like, based on the frame of reference, the math you'd have to do to see how the objects act, like, based on the frame of reference, the plane that they're on changes?
From traveling along point of view, you think you're traveling in a straight line, but from an outside point of view, it looks like you're curving. So there's a difference in relative of perspective there. I think I missed your question. You want to try it again?
It's kind of it. It's
Okay.
like, the map changes if it's your point of view that it's just a straight line, it's Euclidean.
Yeah, the map would change.
Okay.
And so you now have to, so vectors are to scalars like tensors are to vectors. And this is just nonstop tensor calculus.
Oh.
So you
Yeah.
end up with,
I looked in there and
you know, like, you'll have some variable g, and then you'll have u, nu, eta,
yeah,
pi, something like that.
I looked at
which is
my-
different than g, mu, nu, eta, pi.
I looked in my book and I was like, I don't even know what I'm looking at. Like, I mean, if you want it, you can have
It's a
it.
special G.
There's a book by, I think it's Thorne and Wheeler. I found a copy online, a PDF, where they basically it was 2 books in one. That if you are just starting out, you do the first part of every chapter, which generally were the white pages.
Yeah.
And then the dark pages is if you wanted to get into much deeper dive in each topic. So graduate level would be doing the light and dark pages,
Uh-huh.
whereas undergraduates would just be doing the light pages. And, with a lot of physics, it's, okay, I'm good, I'm understanding this, I'm going along, cruising along, everything's good, and then suddenly there's this, it's like you've fallen into a chasm, and you're going, all right, there's a gap there, what happened?
But we've all done that, right? This semester?
Yeah, and then there's this glass.
I thought it was just us.
I think it's at least in my experience, there's a lot of, that gap, and then trying to find someone to explain that gap. And at least there's the internet now, which is really convenient, because, it's like trying to find to explain gyroscopes in terms of the forces involved, as opposed to the angular momentum explanation.
Oh, my
Angular
goodness.
momentum explanation, you can find gobs of it. It's simple looking at it that way, but if someone tries to explain what are the forces involved on the particles, there are not many people who do that. And
My
then-
dad actually designs gyroscopes.
Who did?
My dad,
Ah,
yeah, he's an electrical engineer, works for Analog Devices.
What? That's pretty cool.
Yeah.
can you explain the forces acting on the?
I couldn't. He'd come in here and tell you all about it.
Because there are, I found one source, and I can't find it again, one source which talked about the fact that the disk actually warps. The spinning disk will warp. But I haven't found that again. And then all the other explanations quickly get to torque and angular momentum. Yeah, that's not the issue I'm having.
You want me to call my dad about gyroscopes?
Ask him about the forces involved in the gyroscope, not the torque.
Okay.
Not interested in the torque and the angular momentum, I want force. If you can point me to a source, that would be great.
Is a gyroscope like the thing that locates what direction you're in?
Yeah, pretty much. Once it starts spinning, it tends to want to stay in that orientation, so if you have a gyroscope going, an ideal gyroscope, it's constantly spinning, let's say, that orientation. The angular momentum would be up if it's spinning around like this. It would be down if it's spinning like that. But if it's in a container that is affixed to the rocket, for example, if the rocket starts turning, that gyroscope will still stay standing. So as the rocket turns, that gyroscope still stays pointing in the same direction. And so that way you can always have a bearing of, oh, we used to be the other way around.
Yeah, I think he designs the test systems and he calibrates them so that they stay in their orientation.
Okay.
That's
yes.
what he does.
And that's conservation of angular momentum is the classic explanation for it. That if the angular momentum is in that direction, the only way that you change the momentum is if there's a rotational impulse. In other words, there's some torque applied to it. It's the only way that you can change that. But it's resistance to change.
Because it's made in a way that it always goes back to where it wants to, where it's set at.
Sorry, I got distracted.
Sorry. So they're just like, it's a thing, it moves out of the way, but why does it want to keep going back to where it was? Why wouldn't it just, like, how do they do that with magnets?
All right, well, the practical aspect of
Yeah.
how do they, that I'm not sure. I mean, the physics of it is conservation of angular momentum.
Dang, I'm gonna have to talk to his dad.
Yeah.
I'll call him up.
Like, yo, how do gyroscopes work?
He's not a good teacher though. He'll get very, very angry with you if you don't understand him.
It's okay. I think I can live with it. That's how my grandpa is.
Yeah.
There's just a lot of mad, but if you get through all that, he's teaching you something.
All right, so back to where we were.
Where were we?
Oh, that, we just did the one fixed, one free in. Okay.
Do you need me to hold it again?
Nope, we are done with that. We've done all those. We have in essence have covered, plus the videos, covered what's gonna be on the last test.
That's good.
Just now making it not trivial, so I separate the wheat from the chaff. Or, yeah, that came out wrong. Probably should edit that out. Yeah, I don't deliberately try to make problems hard. But I do find when I give a problem that I think, oh, this is easy, it'll be like a bonus, they can all get it right, and then somebody misses it, and it just makes me very sad.
It's like the beginning of the test 1B. I got like almost the entire concept first page wrong somehow. It was like the uppercut one. I remember
Ah.
that.
Yeah, well,
Well.
it'd be the things that, because I've said you need to know the formula for kinetic energy, and I've asked the question, you know, I give the mass, I give the speed, what's the kinetic energy, and I've had people miss that. And
Me.
I wish there was a formula for that. I have to remember.
if only. There's usually people that got momentum, they knew there's mass and M and V in it, so they used, those that missed it went to the momentum formula.
Wasn't kinetic energy the one that's like 2 times 1/2 the number that was given? I forgot what it was. But I remember the day of the test, that was all that was ringing through my head.
The formula for kinetic
You
energy?
had, not the formula, but you had said something like kinetic energy is.
I knew it was
half-
coming.
What it was.
What is kinetic energy?
1/2 mv squared.
Okay, yeah, that's what I was remembering.
You must fight you.
No, just every day, he's like, what is it, what is it? Say it at the same time.
That's the one person who's quiet in the Zoom meeting.
Oh, there was, sorry, my interjection was louder than it meant to be. There was a master set problem that I went to address from master set 7. Because every single person who did it the hard way.
Oh.
It was the problem dealing with the planet orbiting the sun. And I had it down here. If Earth is 1 astronomical unit from the sun,
Oh, yeah.
what is the mass
Oh.
of the sun?
Dude, that one was
Yeah.
not okay.
So I got sun, I have Earth going around it. I know that the force diagram on the Earth is there's a pull both ways there. This is the force due to gravity. So I end up with G, mass of the Earth, mass of the sun, over the orbital radius squared is equal to mass of the Earth, V squared over R, or omega squared R. I'm gonna do omega squared R. You'll get there either way. So this R here is the radius of the orbit. The question I asked was, what is the mass of the sun? So I'm trying to solve for that. So what do we get rid of? What can we get rid of?
R. 1R.
1 R at least, yeah.
Not in this form.
Oh, no.
We'll end up with an R cubed.
Mass of the Earth.
Yeah. All right, so we can get rid of mass of the Earth. And so if we solve for mass of the sun is omega squared R cubed over big G. R is 1 astronomical unit, as stated in the problem. Omega is the angular speed, which is just changing the angle over time. So as Earth goes around 1 orbit, what is the change in the angle?
360.
Radians.
265.
Over the time, how much time does it take for the Earth to go around?
365 days.
365 days.
Make it simpler.
1 year.
Yes.
I don't
So-
know why we both went for the day.
Yeah.
So omega, we get 2 pi radians per year squared times 1 astronomical unit cubed over G, 1 unit, which was stated in the problem, naturalized units. So we end up with 4 pi squared, that's the math part, and then I just have to keep track of units. That's radians squared, astronomical units cubed per year unit. Done. That's the mass of the sun.
4 pi squared is the mass of the sun
In those units.
in those units. Oh, crap.
If you just keep track of the units, you don't need a calculator. Most people were unsatisfied with that. They did the 365 days, or they did, found out what that was in seconds, or did some sort of translation there, but it didn't have to be that sophisticated.
Well,
So that the astronomical unit has like, you can make it into meters if you need to.
If you had to.
Yeah, okay.
I believe it's the average distance from Earth to Sun,
Oh.
center to center. So anyway, I was hoping somebody would go the easy route instead of trying to make me have to do the math.
Nice example of what AU meant and what unit was, and by then I was lost.
Yeah, I googled it as well. so
I did too.
I just went through.
I watched the tutorial on how to calculate it.
Yeah, that,
Not too good at it.
and it's not wrong to do that, it's just unnecessary. And it doesn't help you at all, but the next version of that, I said, if you keep track of units, you don't have to use a calculator.
Well, I don't know what 2 pi squared is though, so I might have to use a calculator.
That's about 40. Pi squared is roughly 10.
I was joking, but,
Yeah. If you wanted to do one significant figure, it's 40.
okay.
One sig fig.
One sig fig.
I like one sig fig.
You don't know what's better.
Should have done that with uncertainties instead of 7.
7 sig figs. Yeah, that's
Alright.
something.
There is one other bit that I probably feel I should at least address, and that is from Master Set 12. Oh, I do have some things to hand back, I hope I don't forget. Problem number 2. Is that the one? No, not that one. So, is it 13? No, it wasn't that one. Oh, I hope I didn't remove it. Oh, and that also reminds me, to a question I think PJ asked before about plain impossible versus Flubber-esque impossible, or is that Will? Will. I apologize, as I was grading the ones that come in, I thought, oh, of course, plain impossible, you get negative kinetic energy. Flubber-esque impossible, you gain kinetic energy.
No, because you really can't gain energy.
Not without some explosive or some other source.